Hello and welcome to this lesson on convex function. I'm Mohamed Kadem Kari. You may get the PDF of the lesson on my website I indicate here. The outline of the lesson will be firstly to define a convex function, then to give a characterization of convexity of a function, and finally to present the notion of inflection point. So this is the definition of a convex function, but before defining the notion of convexity, we need to introduce the notion of second derivative. Perhaps you may know already this definition, but I remind it for those who don't know this notion. Let f be a function from an interval I to the set of real numbers. We said that f is twice differentiable if f is differentiable and its derivative is also differentiable. We call the derivative of the derivative the second derivative of the function f, and we denote it like this. So this is the second derivative of the function f, which equals f prime prime. So here is an example. Consider this function here, which is a polynomial. Its first derivative equals 6 multiplied by x minus 5. So its second derivative equals simply 6. Before defining the notion of convexity, let's give some curves. Here is the curve of the function x squared, and here is the curve of the function logarithm, which is also denoted sometimes ln. So we aim to characterize the properties of these two curves here and to give a definition showing that the function x squared is convex, whereas the function logarithm is concave, in a sense that will be made precise shortly. So this is the definition. Let I be an interval and f defined on the interval I be twice differentiable. We say that the function f is convex if its second derivative is positive. And we say that f is concave if its second derivative is negative. Observe that the function f is convex if and only if minus f is concave. And this is interesting to deduce properties of concave functions from those of convex function, as I will show in some minutes. So let's apply this definition to our examples. Firstly, consider the function x squared. Its first derivative equals 2 multiplied by x, and its second derivative equals 2, which is positive. So the function f here, x squared, is convex. The function logarithm has first derivative 1 over x and second derivative minus 1 over x squared, so the function logarithm is concave on the set of positive numbers. And these are the two examples I have shown in the curves before this slide. Let's now give characterization of convexity of a function. Here is the main theorem. Let f be a function from an interval I to the set of real numbers, and assume that f is twice differentiable. Then f is convex on the interval I if and only if one of the following properties holds true. The first property says that f prime is increasing. And this is obvious since convexity is defined as the second derivative is positive, so the derivative of the derivative is positive, so the derivative of f is increasing. The second property says that the curve of f is above the tangent at any point of the interval I. So let's draw roughly the function x squared, and let's consider the tangent at some point here. So you see that the curve of f is above the tangent t at this point. The third property says that the image by f of any average of 2 points A and B is smaller than the average of the images. And this will be illustrated in the following slide with a curve showing why this property holds true. Here is an example illustrating the last inequality. So consider the function f to be x squared and consider these 2 points here, a equal 1 and b equal 3. Consider the parameter t to be 1/2, so the average of a and b will be the middle of these 2 points, which is in this case equals 2. So this is the middle of a and b, and the image by the function f of this middle is this point here. So it may be considered as this point. Now the middle of f of a and f of b is the point here on the line joining the 2 points. And our inequality says simply that the image by the function f of the middle is below the middle of the images, which is the point on this line. So it says that the curve is below this line here joining the 2 points A and B. So try to remember this interpretation of this useful inequality. Now we use the fact that the function is concave if and only if its opposite minus f is convex to deduce a characterization of concavity this time. So the setting is the same as usual. Consider a function f from an interval I to the set of real numbers assumed to be twice differentiable. Then f is concave on the interval I if and only if one of the following properties holds true. The first one says that f prime is decreasing. And also, again, this is obvious, since from definition f is concave if and only if the second derivative is negative. So the derivative of the derivative is negative, and this is equivalent to say that the derivative is decreasing. The second property says that the curve of f is below the tangent at any point. So again, let's consider the logarithm function, and let's try to draw the tangent at a given point here. My line is not perfect, but this is a tangent here. And you see that the curve of f is below the tangent at any point. So this is the curve below the tangent. The third property says that for any points a and b, the image by f of the average of a and b is larger this time than the averages of the images. Okay? The image of the average is larger than the average of the images. So you see that this is immediate from the previous theorem. The last part of this lesson concerns inflection point. So I want to define some property here of this point, saying that the curve is going through the tangent at this point. And this is what we call an inflection point. Mathematically, this is defined as follows. So consider a function on an interval I, which is twice differentiable. We say that f has an inflection point at a if its second derivative is 0, and if the second derivative changes sign at point A. This is very important. It is not enough that the second derivative equals 0. We have to check also that the second derivative changes sign at point A. Here is a useful properties. If A is an inflection point of the function f, then the convexity of the function changes at point A. This means that f is convex at the left of A and concave at the right, or vice versa. So in our example, for example, here I have an inflection point at this point here, So you see that for this point, on the right the function is convex, and on the left the function is concave. It has not to be the point 0 precisely. We can also have a function like this, up, and a tangent like this. So again, you can observe that the function is convex on the right and concave on the left. The second property is that the tangent crosses the curve of f. You see in these two examples that the tangent crosses the curve of our function. Okay, this is the end of this lesson. I hope it was clear and useful for you. I wish you good luck for your work on mathematics, and see you later in the next lesson. Goodbye.